All right, we're going to start looking at reviewing for our exam. The exam is really just a subset of what we've done this year. Really the main topics that you should be prepared for is obviously graphs and graph theory, polynomial equations, rational inequalities with the less than, greater than, and then the logs and exponentials we just did. So the exam is only 6 questions, but obviously there's some different parts of these questions. You know, what's this graph, this and that. So it's definitely not going to have every single little topic on it, but it'll have the main topics on there for sure, which is kind of what we have on this review. So if you look at this equation, we have this graph that kind of goes off forever in this direction and stops here. So the domain, remember, is the smallest x to the biggest x. So the smallest x, it's going to go left forever, so it's negative infinity, all the way up to 6, and I would include 6 because there's a closed dot. The range, the lowest y value I see is negative 2. That's at this point here, down here, and it goes up forever, so it is to infinity. So range negative infinity to 6 and range negative 2 to infinity. Is this function odd, even, or neither? This one actually is a really easy question, believe it or not. It is neither. And the reason is odd functions are symmetric to the origin, and even functions are symmetric to the y-axis. And this function is neither. It doesn't have symmetry at all. So obviously that would be one we wouldn't count. C says determine when the function is increasing. Well, it's increasing on this interval right here. It's going up in only this region. Now, when we say when it's increasing or decreasing, we only use the x values. So we'll simply say negative 8 to negative 5, and we will make sure that we use parentheses only. Do not use brackets. That will mark it incorrect. D says evaluate f of 0. So f of 0, that just means that the x is 0. What is the y? Whenever you see this function notation, it's saying, all right, if x is 0, what's the y? So on the graph, here is this point. It's like 0. It's not great. It's like 0 and 3.2. So the y value is simply just 3.2. E is a similar problem. It says, for what values of x does f of x equal 0? So in this case, we want to know what's the x, and we know y is 0, because f of x means the y value. So if you look at the points where the y is, or the x points where y is 0, they're not great. So I would approximate them to be, let's just say, negative 8.7 and negative 7.3. On the test, we'll make sure it's a little clearer. F. If f of 3 equals 2, what point would have to be on the graph? Well, same thing. This is our x, and then the value is our y, so it's simply the point 3, 2. Now, 3, 2 is on this graph as well, so that's kind of nice. There you go. Now, G says, name some points that would lie on f inverse. F inverse, the only thing we really talked about f inverse was just to switch x and y. So I could take any point on the graph and switch x and y. So maybe I take this point, which is 6, 1. That would be 1, 6. Maybe I take this point, which is 3, 2, and I make it 2, 3. Since there are infinitely many points on this graph, there are infinitely many answers you could have. Now, H talks about transformations. Name some points that would lie on 3 times f of x plus 1. Now, I don't really love the way this question is worded, but I put it on here because this is the way the college likes to word their questions about transformations. Remember, inside is going to shift left and right, so this is going to shift right by 1. So the x's will add 1. And then the 3 outside is going to be a vertical dilation. We're multiplying on the outside, so the y's will get multiplied by 3. So all I have to do is take any point, add 1 to the x, and multiply the 3. So let's say I take this 3, 2 point, and that's just an arbitrary point. There are a million points you could do on this. I'd probably give you an actual point on the test. So if I add 1, that's going to get 3 plus 1 is 4. And if I take 2 times 3, I get 6. So 3, 2 becomes 4, 6. If I did another point on the graph, say 6, 1. If I added 1 to 6, I get 7. If I multiplied 1 by 3, I get 3. So I could literally do this for as many points as I want. So this is a general idea of what a graph problem would look like, and this is one that you would be for sure to see on your exam. Another one that we would see on the exam is something like this, where it says, answer the following questions about the polynomial below. Find the roots of the polynomial and put the polynomial in factored form. So the first thing I would do is if I solve this problem is I'm going to graph it in our Desmos or something like that. That is the absolute first thing you should do. So when I graph this in Desmos, I'm just going to kind of sketch what I see. I feel confident we could all put this in Desmos. But the big thing is I see an intercept at -1, 0. I see an intercept at 1, 0. And I see an intercept at 3, 0. These are just x-intercepts. I see a y-intercept way up here at 0, 12. Not that I'm saying that's important. And then the graph is going to look something like this. So this is what my graph looks like. So it says find the roots or the zeros of the polynomial. Well, since it's a degree 5, I'm looking for 5 zeros. So my zeros that I'm looking for, 1, 2, 3, 4, 5, I already know 3 of them. I know -1, I know 1, and I know 3 because those are x-intercepts. So really, I'm just missing 2 of them. So if you recall how we dealt with this, we would divide these out. So we'll take -1 divided by 1, -3, 3, -9, -4, 12. We know the remainder should be 0 when we get to the end, and we're just going to do this multiple times. So that's -16, that's 16, that's 12, that's -12, that's 0. So now we'll divide the next one. It doesn't matter the order, so now I'll divide 1, because I divided that one. Now I'll divide 1 into the remaining numbers. 1, 1, -3, -3, 4, 4, -12, -12, 0. And then finally, I will divide the 3, 1, 3, 0, 0, 4, 12, 0. Now, the whole benefit is when you get to the end, and I'm not sure I give you a degree 5, it'd probably be a degree 3 or something a little more simple. We know this is x squared plus 0x plus 4 equals 0. So I just have to solve this. So I'll subtract 4, I'll take the square root. So x equals plus or minus the square root of -4, which is 2i. So my other zeros are -2i and 2i. So those are my 5 zeros. And it makes sense that the last two would be imaginary because I don't see them on my graph. So whatever ones you see on your graph, you'll divide out, you'll get a quadratic, and you'll solve that. So end behavior is kind of a small topic. It's on their review, so that's fine. I'll go ahead and do it. So as x goes to infinity or x goes to negative infinity, it's basically saying where does the graph go? So as x goes off to infinity, is the y going up or down? Well, it's obviously going up. So we say as x goes to infinity, f of x goes to infinity. And as x goes to negative infinity, so as x goes left, the graph is going down. So f of x is going to negative infinity in this direction. Finally, this says what happens to the graph at all 5 zeros? Well, in this case, they all cross. Remember, if a 0 touches, then it has an even multiplicity. So we put a power on it that's even. Okay. So number three talks about a polynomial equation as well. So it says it has a degree 3 polynomial, so we know there have to be 3 zeros, and it gives us 2 of them, 1 and 2i. So the one we're missing, obviously, has to be a pair, so it has to be negative 2i. So that would be pretty much what you'd have to do. If you wanted to actually write the equation, you certainly could. F of x equals x minus 1, x minus 2i, x plus 2i, because remember, the zeros and the factors are always the opposite. But again, I wouldn't worry too much about that, about foiling it. This would be sufficient if there was a question like this on there. The big thing is knowing that if you have one complex zero, there has to be another complex zero paired up somewhere with it. So we definitely have a graph problem, we'll definitely have a polynomial problem, and there definitely will be a rational function problem, because this is something we talked about a lot. So rational functions, remember, we always approach these first by factoring the top and bottom. So the top is just x minus 3, that's fine. The bottom I factor two numbers that multiply to negative 3, add to negative 2, or negative 3 and 1. So I can see that the numbers that x can't be are what makes the bottom 0, which is 3 and negative 1. Now obviously something will cancel here. You'll notice that we cancel out an x minus 3 to give a reduced form of simply 1 over x plus 1. So the 3 that cancels out, that is going to make our whole. So that'll be for D. So we can jump down and do that first. So I know there's going to be a whole at 3 comma something. And how I find the y value, remember, we will plug in to this reduced form rational function up here. After you cancel it out and get your whole, everything gets plugged in there. So 1 over 3 plus 1 is simply 1/4. So this thing has a whole at 3 and 1/4. It also says what are the vertical asymptotes. Vertical asymptotes are what makes the bottom 0 when in lowest term. So what makes this bottom 0? And that would be x equal negative 1, because negative 1 plus 1 is 0. Finally, it says what is the horizontal or slant asymptote. So generally, if the degrees are the same, we would just divide the leading terms, but it's not. In this case, the bottom is bigger. This is absolutely the easiest case. If the bottom is 0, it's always a horizontal of y equals 0. Every time, every time. Now E is a little trickier, and it kind of incorporates the last kind of problem we did with rational functions here, which is what are the values when g of x is greater than 0? So for this, we're basically trying to figure out when is x minus 3 over x minus 3 x plus 1 greater than or equal to 0. So this is when we have to use our sign chart. So our sign chart, we look for zeros and we look for excluded values. Now in this case, zeros would be what makes the top 0, which is 3. And excluded values, which would make what makes the bottom 0, which is 3 and negative 1. Now since 3 appears in both, we're going to count it as an excluded value and not worry about it as a 0. But for our purposes, it's going to be the same thing. Now the key thing for an inequality, and this is probably the most missed question on test 2, is you have to draw your sign chart like this. We'll have negative 1 and 3, which breaks us into 3 regions, A, B, and C. We'll pick a point in each region. I'll pick negative 10, 0, and I don't know, 10. And I'll just plug it into the function up here. Now the nice thing is, since these do cancel, I could just really plug them into 1 over x plus 1 and see if I get a negative or a positive. So if I plug in negative 10, I get negative 10 plus 1, that's 1 over negative 9, so that is negative. If I plug in 0, I get 1 over 0 plus 1, that's positive, and I don't care what the number is, to be honest. And if I do 1 over 10 plus 1, that is positive as well. Now in this problem, I'm looking for regions that are greater than 0, which are these two regions. So now, based on these two key numbers, I'll just write my two solution regions. Now, negative 1 and 3 are excluded, so I'll just put those in parentheses. So negative 1 to 3 and 3 to infinity. Those are the two regions that would make this inequality true. All right, so we're going to look at graphing this log function, 3 log 4 x minus 1, and state its domain and range and see if it has any asymptotes. Okay? So, if you look at this function, you could certainly graph this in Desmos, but I'm going to graph it by hand, knowing that if I have some parent function log base 4 of x, we've done this several times, then I know 1 over the base negative 1, 1, 0, and 4, 1 are kind of base points. And then I can just see what happens to my graph. Well, I know it gets shifted right by 1, and I know the y's get multiplied by 3. So I'll just take all the x's and I'll add 1 to those, and I'll take the y's and I'll multiply by negative 3. So that's still 0, and that is 3. Now I also know this starts with an asymptote of x equals 0. So only things that change the x will change my vertical asymptote, so it'll be shifted by 1. Now again, most of you are just going to use the calculator to kind of see how it works, but not very difficult to do it without it. So we're going to go 5 fourths and negative 1, which is like here. 2, 0, and then 5, 3, which is like here. So my graph will look something like that. So this is one that you want to make sure you get this one right, because you could check in the calculator. There's really nothing to it. So 6 is when we're talking about combining logs. Now we have those properties of logs. We know n log x is log x to the n. We know log of x plus log of y equals log of xy. We know log of x minus log of y is log of x divided by y. So if we do this, we know we'll take the exponents up when we're putting it as a single log. So this will make us log 2 minus log x cubed plus log y seventh. Now, the easiest way to do this when you're writing it as a single log, it'll be log. Anything that's positive is going to go on the top. So this 2 will go on the top, and this y to the 7th will go on top. And then anything that is negative will just simply go on the bottom. So now I've written it as a single log. You might have a problem like this. It might be incorporated into one of the equations that we'll see on the next page. So we just did these kind of equations, so nothing too surprising, hopefully. Obviously, if it's an exponential equation, our goal should be to get the bases to be the same. So I obviously can't get the bases the same here, so I'm going to take the log of both sides. And obviously, since it's e, it's a smart idea to take the natural log. So we get natural log of e to the 2x equals natural log of 5. I'll bring the 2x down and get ln e equals ln 5. But then remember, ln e, this is just 1, so you can kind of ignore it. So x is simply going to be the natural log of 5 divided by 2. Now, if you want to find out what that is, that's fine, but this would be sufficient as well. Now for b, you could certainly do this one a similar way. You could take the logs of both sides, but there's a much simpler way to do it. Because remember, we love to get the bases the same. And 64 is just 4 times 4 times 4. So 64 can be written as 4 to the third, and we already have a 4 on the other side. So really simply, if you can get the bases the same, this makes life much easier. So if you get 4 to the first, x plus 2 equals 4 to the 3 times 3x minus 1, since the bases are the same, you can just set them equal. And now this is just a linear equation, no quadratics, we just have to solve it. So we have x plus 2 equal 9x minus 3. We'll add 3 to both sides. So I'll add 3 and I'll subtract x. So we get 5 equal 8x. And I'll just simply divide by 8. So 5/8. Now this is certainly something you could do with logs, but if you can make the bases the same, that makes life very, very simple for us. All right, final problem. Log base 8 of x plus 3 equals 2 log base 8 of 2. So if some of them have logs, my goal is going to be to get everything with a log on one side. So I'm going to subtract log base 8 of 2 from both sides. Now the reason I'm getting all the logs on one side is I can now use those properties. Log base 8 of x plus 3 over 2 equals 2. And I can't cancel the log out because I don't have log on both sides, but what I can do is switch it to exponential. So it's 8 to the second power equals x plus 3 over 2. So that's 64 equals x plus 3 over 2. I would just simply multiply both sides by 2. So I'll get 128 equal x plus 3. And then just subtract 3. So x is 125. So that's all there is to it. This is a pretty good representation. It'll be on your final. Final probably not quite this long, but this is what I would expect to see for your final.